Well, good morning or good afternoon or good evening, depending on where you are today. Thank you for joining us for our inaugural Construx Lunch and Learn, where the topic is responding to the intellectual phases profile. I'd like to start by setting some context on what we're doing with these Construx Lunch and Learns. I'm your presenter. My name is Steve McConnell. You might know me as the author of Code Complete or through my most recent book, More Effective Agile. Today, really, though, my role is as CEO of Construx Software. And Construx, we have a belief that we should be trying to give back to the community that has supported us, and our community really is the software community. So I wanted to say a couple words about why we're doing these lunch and learns. In 2009, we had the SPEAR program during the recession, which gave free public seminars to software professionals who had been laid off from their jobs. And we thought that this was a really good way to give back to the community that had been supporting us. Now we have a situation where, due to our very unusual circumstances, we have lots of software professionals who are working from home. And our hope is that the Lunch and Learn programs can serve a couple of purposes. One is we'd like to give people just a break from the rest of what they're doing working at home and maybe give them a change of pace and something that's interesting and educational. The other is that our real hope is that people are able to use these lunch and learns to develop or establish or just increase a sense of community. Our hope is that teams will take these lunch and learns together, that you'll get together after the lunch and learn and discuss what you heard during the lunch and learn, and that you'll use that to improve your performance as a team. These lunch and learns will be ongoing through the end of April. Please feel free to share the link at the bottom of the screen with your friends. It's just construx.com/lunch. And we're glad to have you here. So let's go ahead and get started. In terms of logistics, again, thanks for joining me. You should be able to type in questions throughout the session. I will be monitoring questions as they come in, and we'll take time to answer questions depending on how they come in and what the questions are and how relevant they are to the content. If you see me looking off to the side here, it's because that's where I'm looking to check on the questions that are coming in. I would say avoid hitting the space bar on your computer. That pauses the presentation. I'm anticipating getting some questions about, hey, my presentation froze. It's probably because you hit the space bar. So just hit it again and the presentation will resume. So let's go ahead and dive in. The outline for the talk today is what are intellectual phases. So I want to describe the intellectual phases model. I want to describe how to use the intellectual phase model to understand your specific flavors of uncertainty. And I want to talk about how to use the intellectual phases to make some decisions or get some ideas about how to respond to uncertainty in your case. So let's just start with that first topic then of what are intellectual phases. This talk is really based on my 4 factors life cycle model. In the 4 factors life cycle model, as it says, there are 4 factors. The 4 factors are size, human variation, uncertainty, and defects. Uncertainty, all of these factors matter. I think these are the 4 critical factors for understanding how to run a successful software project and how to understand where problems come from and so on. The intellectual phases model, I think, applies in large part to the uncertainty factor in the 4 factors model. So I think that this topic is an important topic. It gives you a model for understanding in a broad-based way the role that uncertainty plays in software. I think it helps begin to understand some categories of uncertainty. We can certainly go into that in more detail than we're going to be able to do during this lunch presentation. But I think in general, it gives you a useful way to understand general approach to dealing with uncertainty as well. So let's dive in. The intellectual phases are what I'm going to call discovery, invention, and construction. And we could use more traditional labels like requirements or design or implementation. But in each of these cases, I think that requirements is each of these activities or phases, and I'm going to use those terms interchangeably here. And I understand that most of you are working in iterative development environments where you are interleaving these activities quite a bit. And I'll describe why I still think it's okay to talk about these as phases in a minute. But I think each of these activities of requirements, design, and implementation has a primary characterizing challenge. And so I think the primary characterizing challenge of the requirements phase is actually discovery. That is to say, we could say that there are other activities in requirements. There's specifying the requirements, that is writing them down or capturing them somehow. There's listening requirements. But I think that the thing that's the most challenging typically for software projects is discovery. That is trying to just figure out what the requirements are, discovering. That's where the uncertainty comes from. Likewise, in the activity of design, we also have activities related to writing down the design that we come up with, reviewing the design, inspecting it for errors, and so on. But I think the primary defining attribute of design that characterizes its uncertainty is this role of invention, and that is the question of, can we even invent a solution to the design challenge that we discovered in requirements? And then in implementation or construction, I do think that software construction is the primary challenge here, and I'll have some more words to say about that momentarily in terms of where the challenges come from, where the uncertainty comes from, or where it does not. So I think these are the defining source of challenges in the areas of requirements design and implementation. So I said the word phases. I know it's almost like, oh, you can't say the word phases, that's waterfallish. Well, is it really waterfallish or not? It's kind of waterfallish, but I think that the real waterfall, or what we're really talking about, is sequence and activities. And some of these activities kind of have to be done in a certain order, whether we're doing them in huge batch mode like in the waterfall days, or tiny batch modes like we would be doing them in Kanban, or medium-sized batch modes like we would be doing them in Scrum. Traditional waterfall looks like this, where we start at the beginning of the project with a software concept, and then we try to do all of the requirements, and then we try to do all of the architecture, and then we try to do all of the detailed design, et cetera, et cetera. And there's lots of commentary about, did any projects ever actually work this way, and so on. But the basic idea here is that we're working through these in some kind of rough order. And I think if you think about it, it's actually pretty hard to begin doing top-level design for something before we have any idea what that thing is. So there's a sense in which at least a little bit of requirements has to precede a little bit of architecture. Likewise, we can't really begin coding until we know what we're coding for. And so some sense of requirements needs to precede that. And if we're going to code under an overarching architecture, some architecture work needs to precede that as well. This traditional, I mean, at this point, very old and out-of-date presentation of how activities flow, I think doesn't do a great job of representing how work really flows on software projects. And so what I think the intellectual phases model, which is not what I just showed you, what I just showed you is the old-fashioned waterfall diagram, but the intellectual phases model that I am going to show you represents the general emphasis and flow. I emphasize the word general emphasis and flow of work on a software project. And of course, that gets fine-tuned through our iterative planning and so on. So the intellectual phases, I'm going to draw in terms of this graph. And you'll notice on the horizontal axis, or the x-axis, I've got schedule. That makes sense. That's intuitive. On the vertical axis, or y-axis, I have focus. The word focus is a deliberately chosen word. I do not have the word effort or cost. Focus is really just intended to be a little bit of a catch-all, general, somewhat vague phrase that talks about what is our main emphasis or focus at different points in the schedule. And as we work our way through the project, what we start with is requirements. And again, the primary challenge here is discovery. So I'm going to refer to this mainly as discovery rather than requirements. And early in the project, we tend to put, it looks like my requirements line's not actually showing up here. Anyway, there should be a line, which I will just draw on here. And so we should get a requirements line that looks kind of like that. And so what this says is that early in the project, we tend to be putting focus mainly on requirements. And as we work our way through a release cycle or a project, then our emphasis on requirements diminishes. Now, it can stay kind of steady state at a higher level. So let's say that we, depending on where we are, we could settle into some kind of steady state requirements where we have more than zero emphasis as we work our way through the project. That all just kind of depends. But the point is that early in the project, we're putting a disproportionate emphasis on requirements. Secondly, after we kick off maybe some initial requirements, maybe initial population of the product backlog and so on, then we change our focus to invention. And with invention, we are inventing the solutions to whatever requirements we discovered we needed to deliver. And then finally, our emphasis changes to construction, and that's where we're constructing or implementing the solution that we invented in design and that we discovered we needed to invent in requirements. And there are several significant aspects of this intellectual phases model. I'll call your attention to the fact that the flow in very general way goes from discovery through invention, through construction. But I'll also call your attention to the fact that there's overlap in these phases. So we have overlap between discovery and invention. We have overlap between invention and construction. And that's significant, and I'll talk about that more in a minute. So let's talk about the implications of the diagram. One implication is this flow generally from left to right. One implication is that invention, and this is important, invention tends to begin before discovery is complete. So we still have some discovery going on here, but we also have invention that's starting here, or actually usually all the way back here. And the same thing is true for construction, where construction is going to begin before invention is complete, but it's also probably going to begin before discovery is really complete. And so we have some overlap in activities. Then the other interesting thing is that some upstream work depends on downstream work, right? Of course, normally downstream work depends on upstream work. But in this case, we actually have cases where some downstream work is going to depend on conceptually upstream work. So for example, we might have a requirement or discovery that depends on the technical feasibility of a solution. That is, we want to have a requirement, but if we can't actually do it, we're not going to have it. And so we actually have to do some technical feasibility investigation or invention before we can really pin down the discovery. And likewise, sometimes our design approach is going to depend on, well, how difficult is that design to implement in the implementation technology or in programming language? And so we have cases where the invention can depend on implementation details. So this is kind of an odd way of looking at it maybe, but there are cases where upstream work depends on downstream activities, which is a little backwards from what we sometimes think. And I would also say that I think there's usually more potential uncertainty in discovery and invention than there is in construction. I think if we do a really good job of trying to attack uncertainty during discovery and during invention, then we probably are not going to have too much of a challenge in construction. A lot of times when people think there's a lot of uncertainty in construction, it's really uncertainty that arises from discovery and invention, but that's being discovered during the construction activity. And so we see a lot of times where the uncertainty in construction ends up being misdiagnosed. And I think that this idea of latent problems, so we have latent discovery or latent invention issues is really a key idea. If we don't do a good job of attacking uncertainty in discovery and invention, then we can very much end up with those latent issues creeping into construction. Okay, so what does it mean that we have all this overlap? I've shown you the overlap. What does that really imply? Well, we in software have this notion of a wicked problem. And a wicked problem is defined as a problem that cannot be fully defined until it is at least partially solved. We have all kinds of these in software. So the classic example is the user who says, I don't know what I want, but I'll know it when I see it. So in other words, solve the problem, bring me the solution, and I'll tell you whether you solve the right problem or not. That is a classic wicked problem in software. Another way of putting this is a wicked problem is a problem in which the problem space and the solution space are at least partly overlapping. And so when we see these zones where there's some amount of invention that's occurring while discovery is still going on, that's indicative of a problem space and solution space at least potentially overlapping. Similarly, with part of the construction space overlapping the invention space, there can be some overlap, and then where all three are overlapping, that could be a significantly wicked problem indeed. So software development, I think software projects are often characterized by having at least some wicked problems. I think sometimes we confuse ourselves and think that software development is 100% wicked, and of course that's not true. There are lots of problems we solve in software that have been solved many times previously, and so it's not the case that 100% of the project is wicked. But it is the case that some of it is wicked, and in fact, trying to ascertain on our specific projects how much of it is wicked is a key part of understanding uncertainty and then setting ourselves up to effectively address uncertainty. If we sort of treat it as one one homogeneous mass where the whole thing's uncertain, that doesn't give us a very effective approach. Likewise, if we treat it as if nothing's uncertain, that doesn't give us a very effective approach either. And so we can manage this through our selected approaches, which we'll get into in a little bit. So this is a key question. Should we just accept software projects' wickedness? And obviously my answer to this is no. What we find is that because of all this overlap, which I just drew diagrammatically, wherever we actually see overlap, that means dependencies. That means the chance that there is uncertainty, that some of the upstream work or downstream work, depending on which it is, where we have dependencies and uncertainty. If the uncertainty gives rise to a change in the dependency, then that's going to have a ripple effect into all the activities that depend on that uncertainty. And that, of course, suggests that there's risk on the project, and that risk is basically in software manifests as rework. That is, if we have a dependency and that dependency changes, guess what? We've got some rework to do to correct from that dependency, and that leads to higher costs and longer schedules and lower quality, and in general, just all kinds of challenging dynamics on our software projects. So the version that I've been showing you of this diagram, I conceive as essentially software in its native state. That is to say, in its native state, if we don't take any action to attack uncertainty or identify and work with it, we're going to have this overlap that I've shown in these areas. So what we want to do is we want to take active steps to separate those curves and reduce the overlap. That is, if we can actually attack the uncertainty, then we reduce the chance that there's downstream work that depends on uncertain upstream work, and that can disrupt the downstream work if the upstream work changes. So I'd like to change now to the second part of the talk, which is how to use intellectual phases to understand your specific flavors of uncertainty. And here I think what we need to understand is that the degree of overlap of the intellectual phases changes, and the degree of challenge within each intellectual phase also can be different. And it's useful to us to understand how big is the overlap and to what degree are we anticipating challenges arising from these different phases. So let's talk first about the degree of overlap between the phases. And here it looks again like I somehow lost my line, but I'll draw that back on here for you. So the nominal overlap is as shown, where we've got really pretty significant overlap, which I think I've probably talked about enough already. And I think if we don't take any action to try to drive the curves apart or identify and attack uncertainty, then we're going to have some degree of overlap as shown in this basic diagram, but it's not too extreme. In an ideal world, and this is kind of the assumption the waterfall model was based on, we would have effectively zero overlap between the activities of discovery and invention and construction. And this would be great because we could actually conclude all of our discovery before we really needed to begin any of our invention. As we're working on invention, we know that we've completed the vast majority of discovery, and so there's very little chance that something we missed in discovery is going to disrupt our invention work. And likewise in construction, when we get there, we've completed the vast majority of our discovery and invention work, so there's hardly any chance that that upstream work will disrupt the downstream work. And so that would really be ideal. Good work if we could get it. The waterfall model was really based on the assumption that this could be done on every project. And I think that what we found over really the last 30 years is that we might be able to do it from time to time, but even with really good, disciplined, well-intentioned work, we often can't get to this ideal state. And so our project approach really ought to be based on the expectation that there's going to continue to be some overlap between discovery and invention and between invention and construction. And our approach needs to be resilient in the face of that overlap. So anyway, that's just the ideal that we strive to move toward. We don't start in the state shown here, but I think with the right kind of work, we can actually move our project through identifying uncertainty and attacking uncertainty. We can take a project that starts out looking like this, and we can move it toward a project that looks more like this. And that's a useful thing to do in terms of reducing uncertainty, reducing errors, reducing rework, and giving ourselves a more predictable project and a lower cost project. So worst case overlap, where we have a truly wicked problem, is where we have high degrees of overlap between discovery and invention and construction. I've drawn on the discovery line here in red. And this indicates all kinds of overlap where the problem space massively overlaps the solution space, and the idea that the problem cannot be fully defined until it's at least partially solved is just manifest in spades in this version of the diagram. I don't really think we see that worst case overlap all that often. But in the cases where the project, I think sometimes people think that that's their life, and that happens all the time, and I understand and I empathize with that feeling. But I think really when people are feeling like they're here, they're probably more like in the nominal diagram. If your project truly is in that state, then I don't have great news for you, in that I think that you have a high risk of failure of that project. Even if you employ active practices to attack and reduce uncertainty, it's unlikely you're going to reduce it to a low level. And so you have to really take an approach that says you're going to A, super actively attack uncertainty, and B, plan to still have a lot of uncertainty left over even after you do that. And I think that what we also see, though, is that a project that starts out in that nominal case that I've defined, if it's not managed very well or conducted very well, if we just let inertia or entropy set in, lower risk projects can often degrade toward that highest risk scenario just through ineffective development practices. And so I think it's important to understand when I say what the project looks like in its native state. Bad project approaches can easily make projects look worse than that. And we see that, of course, all the time. And I've talked about, can we get to the ideal in all cases? And the answer really is no. But let's talk about how much we can reduce the overlap. So I think if we start out in a nominal case, we often can move it toward pretty close toward the ideal case. And again, I'll draw in the missing lines here. Oops, let's not do that one. Let's see here. We'll erase that one. So we can get to the pretty close to the ideal case if we employ the right kinds of practices, which I'll talk about in a little bit. So if we start out in this extreme case where we have massive amount of overlap to begin with, maybe we can get to the nominal case through active approaches to uncertainty. And I think that's possible in most cases, but it requires active work. We really, it's not going to happen automatically. The automatic result of this is basically failure. So if we don't take active steps in this case, we're really in trouble. So is it possible to take this worst case scenario and move it toward the best case scenario? I think usually not. I think usually, maybe once in a while we could achieve that level of uncertainty reduction. But in most cases, we should resign ourselves to working on a much higher risk project than the one shown here on the right side of the screen. So we can reduce wickedness to some degree. To summarize, we can't reduce it entirely. And so it's useful to have project practices that are predicated on the idea that we're going to continue to conduct the duration of a project with some degree of uncertainty on the baseline of that project. When we have a high degree of wickedness natively in the project, I think we should be asking pretty early in the project whether we can have a business justification for a project that's going to remain at least a moderately high level of risk over the course of the entire project, despite our best efforts. And in some cases, there's a good business case for taking on a project that's high risk. In other cases, there really isn't a good business case for taking on such a high risk project. And if we're asking the right kinds of questions about uncertainty early in the project, that gives us the ability to potentially shut down a project that's a bad idea, or it might be a good idea, but we just don't have the ability to conduct it in a low enough risk way. We can make that decision to shut down the project early, save our company a lot of money, and free up resources to focus on other projects that we have a higher chance of being successful with. So let's move then to the topic of the degree of challenge in each phase. So far, I've shown this diagram as though the curves are about the same height, where we've got this focus word on the left, and it sort of says we've got a high level of focus on discovery early on, an equally high level of focus on invention, equally high level of focus on construction. So these are all kind of about the same level of top level focus. I think this significantly mischaracterizes where the challenges come from on software projects. So I'm now going to show you a variation of the diagram where we can draw out some implications of challenges coming differently in different areas. So we could, for example, have a project that has challenges coming. Let's see. No, in fact, I drew that wrong. Let me erase that. So we could have a project where most of the challenges are coming from discovery and not many challenges are coming from invention or implementation. We could have a project where most of the challenges are coming from invention and not very many challenges are coming from discovery or construction. We could have a project where most of the challenges are coming from implementation. I think that's rare, but we could have a project like that where there really aren't many challenges coming from either discovery or invention. Similarly, we could have projects where we have high challenges in discovery and in implementation, but not in invention. We could have projects where we have high challenges in discovery and invention, but not in implementation. And we could have a project that has low challenges in discovery, but high challenges in invention and implementation. I'll give you examples of this to follow. So let's see where these variations, let's take a look at each of these cases. So this first case, where we have high challenge in discovery, lower challenge in invention and construction, example would be like an in-house business system where we've got like new warehouse management system or a new cell phone pricing plan, something like that, where the challenges might come from maybe the politics of defining the requirements, or but the technology and the design are pretty straightforward and easy. We're working on a familiar platform. It's familiar from a design point of view. There's nothing super challenging about this except getting the requirements right in the first place. And so that would be an example of this first case. An example of high challenge in invention and a lower challenge in discovery and construction would be something like scientific research software, where it might be super easy to define what the physics problem is or what the chemistry problem is, but actually coming up with the design to effectively implement that challenge ends up being, that's where the challenges lie. And then once we figure out what the design is, essentially what the science is in software, then the implementation is actually pretty straightforward. So this would be an example where specifying the problem is pretty easy. Coding the solution, once we discover the solution, is easy, but trying to figure out what the solution is, that's really the challenging part. Another example of that might be a systems integration project where specifying it's pretty easy, which is we need to bring these two systems together, and then actually coming up with a design for how we're going to merge these two disparate systems. That's the challenging part. And then once we specify that and figure out how it's going to work, then the actual coding work ends up being pretty straightforward. So that'd be another example of this high challenge in invention, lower challenge in discovery and construction scenario. The scenario where we have high challenge in construction and lower in discovery and invention, one example would be a port from one platform to another, where the requirements are pretty easy. I mean, I almost just said the requirements right now. The design might be pretty easy as well, which is we just need to do a language translation. And the work really is just cranking out the line-by-line translation or module-by-module translation from one system to the other. Another example might be a large upgrade project for a mature product on an existing design and code base where we have good alignment on business objectives. So if we have good alignment on business objectives, that means the requirements effort or uncertainty is low. If it's a mature existing design and code base, that keeps the design challenge low. And this is really another example of a project where really the mission is just crank out the work. So the high challenges in construction, and normally remember I said this axis is focus. So for discovery and invention, really the challenges arise from uncertainty. So we would tend to have uncertainty here. This is really less uncertainty, it's just about work. So if we've actually done a good job earlier, the challenge here is just going to come from managing the details of the work, less from managing uncertainty, typically. So let's look at the case where you have high challenge in discovery and construction, but lower challenge in invention. A specific example of that would be similar to the one I just gave you, but it's a large upgrade project for a mature product where we understand the design and code base well. But let's say we have lots of politics around the business objectives. That could give us high uncertainty in the discovery phase. That doesn't mean we have uncertainty in the design phase, but it means that this now is going to become a more defining aspect of the project. Another example might be a system programming project with implementation in an older technology like C or assembler. The reason there's uncertainty here is just because we don't necessarily have the good staff skills in the technology anymore. I mean, C is still fairly common in some contexts. Assembler is pretty uncommon almost everywhere these days. There are exceptions, but mostly still pretty uncommon. So the uncertainty here is really kind of a technology uncertainty. And then but there's no real necessarily uncertainty arising from the system programming if it's in a familiar area. So high challenge in discovery and invention, lower challenge in construction. Example here might be ERP implementation project, and these are just classic in terms of, we have requirements problems in terms of trying to figure out what the business rules actually are. We have integration issues with existing systems where we end up with all kinds of design issues because of the interfaces. Once we get all those design and business issues settled, then the construction stuff doesn't tend to be super challenging. It's crank it out. This is a great example of a case where people often misdiagnose challenges in this area, challenges that are really coming from one of the other areas. They just don't happen to show up until this area, until the construction activity, because not enough work was done in the earlier areas. Example number 2 would be a greenfield project in a new state-of-the-art technology area. The greenfield aspect of it suggests that there could be a lot of uncertainty in the discovery. This new state-of-the-art technology suggests there could be a lot of uncertainty in the design. Once we figure out how the design works and what's possible, then we can kind of crank it out. This is another case, I think, where we often see a misdiagnosis of the challenges really being construction challenges when they're not, in fact, construction challenges. They really are, in this case, mostly challenges related to us not understanding what was possible. We could quibble about, well, is that really still a construction challenge or not? But I think the key point is that we're trying to recognize where is the uncertainty coming from and deal with it where it's really coming from. It's not a coding issue. It's not a testing issue per se. It's a technology issue, and we need to address it as such. So high challenge in invention and construction, lower challenge in discovery might be natural language English to French translator. Now I can make that specification, translate English to French with at a level of fluency. Pretty easy to set the requirements for that, but the discovery, or rather the invention aspect of that, can be challenging. Obviously, it's taken us as an industry many years to get reasonable work through online tools for that in text. And even then, I think sometimes the results are pretty comical. But and then I'd anticipate possibly a significant amount of construction effort for that as well. Example number 2 might be something like an air traffic control or other safety critical system. In these situations, often the requirements are super clear, and the challenge in design and implementation is less about uncertainty in each of these areas and just more about perfection. Because of the safety requirements, we really have to make sure that the work that we do is near perfect because of safety reasons. So the challenges are coming not so much from uncertainty, but in this case from a different area. So the key point here is when we look at all these examples of where the challenges come from, and we've gone through quite a few examples of where challenges might come from, we do not have to just lie back and say, too bad, there are lots of challenges, we can't do anything about it. No, we do not have to take these challenges passively. And I think one of the problems that we see in software is teams thinking that teams using one-size-fits-all approaches where they think, well, we use this approach on every project, and so we'll use it again on this next project, and it worked fine on the last project. It'll probably work fine on the next project. And the problem is, as I've just gone through numerous examples of, the challenges come from different areas on different kinds of projects, and so we need to respond differently to actually address the challenges in these different areas. If we try to do a one-size-fits-all approach, either we're going to be too lightweight in some cases when we have more challenges in an area than we're used to, or we're going to be too heavyweight in all cases, where if we if we assume that every project is going to have massive challenges in every area, and we have a really strong response in each of those areas, that's going to be overkill for most of our projects in at least one of the areas. And so the one size fits all is just not going to work very well. These projects should not be treated as the same. If we have a high level of overlap in the projects, we should not treat that the same as a project where there's hardly any dependencies or overlap in the activities, or hardly any wickedness in the activities. Likewise, if we have low challenges in all areas, that's not the same as if we have high challenges in, say, discovery and invention. And we should not address those projects as if they're the same. If we have high challenge in the discovery area, we should not address that as the same as though it was high challenge in discovery and high challenge in invention. And likewise, we shouldn't address a project that has really high overlap or high wickedness across the board the same as a project that has medium, or I would really characterize this as nominal overlap throughout the project. So given all this, the fact that I think we now have a basis for understanding that challenges can come from different areas in a software project, and the degree of overlap can also be different. And so if we have a high challenging area that has high overlap with the area that depends on it, that suggests there could be a potential for a great deal of rework. So if I have, if I go back to one of these examples with low overlap, if I have low overlap, I'm not really that concerned about this invention activity, or I'm not concerned about errors in requirements upending my invention activity, because there's just not that much potential for it. If I have this kind of overlap, then I'm very concerned about dependencies in discovery upending my invention work, because I'm beginning my invention work way before I have all the details of discovery pinned down. So there's a huge chance of errors creeping in, changing the upstream work, and then that rippling through into the downstream work. So let's now move to the final part of the talk, which is how to use intellectual phases to respond to uncertainty. I think a large part of this is actually previewed significantly in my comments up to this point. Certainly just diagnosing it already, I think, gives us some good suggestions and ideas about how we might respond to uncertainty. But let me try to add some more specifics in terms of how those responses might be done. So I think that we're going to base our response on three considerations. One is the degree of overlap between the activities or phases, the degree of wickedness, and I've previewed that topic quite a bit already. The second is the degree of challenge in each phase, and I think I've previewed that topic quite a bit already too. And I also think it's useful to look at the challenges seen through the lens of the 4 factors life cycle model. And in each of these areas of discovery, invention, and implementation, we should be thinking about the size factor. Is the size of the project, the size of the work, or the size of work in that area going to be something where we have to deal with on its own, meaning is the largeness of it in itself an issue? We should be looking at it through the defects lens, and that is, what is the potential for defects to creep into our project from this area? So depending on whether we're talking about discovery or invention or implementation, there's a lot of uncertainty that tends to imply a higher potential for defects. So we should be looking at the defect potential and what we're going to do to make sure we detect defects in a timely way and correct them and not let them all just stack up to the end of the project. We should be looking at uncertainty, which has been the main focus of the talk so far. I'm not going to repeat that too much at this point. And then we should also be looking at human variation, which is basically how good are the humans, not just in general, but how good are they at the specific activities of discovery and of invention and of implementation. And if we have extra challenges in any of those areas, we might be looking at, well, how can we leverage human variation to respond effectively to the challenges in each of those areas? And then there are interplays between these as well. If we have lower skilled staff, that creates the potential of more defects. If we have higher project size, that creates the potential for more defects. More uncertainty, that creates potential for more defects. If we have low skilled staff, that inserts uncertainty into our project, and so on and so on. So here are some ideas. If we have a low emphasis project, or low emphasis in discovery, invention, and construction, we could potentially use relatively lightweight practices. So we could do our requirements work through notes or post-its or whiteboard pictures. We could do informal reviews of requirements, as maybe just sitting around and talking about them. We could have the requirements work done by relatively junior staff. And so that would be, if we really truly need low emphasis in the discovery activity, these are the kinds of lightweight approaches that we might take. For invention, same thing. We might document our invention with just design notes, post-its, or whiteboard pictures. Maybe we have informal reviews. Maybe if we have super senior staff, we might not even need that. Or we could have maybe junior designers if the invention challenge is just not that significant. Similarly, in construction, we could perhaps use solo development, meaning individual people working on their own, not necessarily doing any kind of pair programming or other kinds of collaborative construction techniques or reviews. We could do informal reviews if that's not quite good enough. And maybe we just focus on unit testing and integration test. And if there really is low emphasis in the construction area, that might be all we need. And again, junior staff here. If it really is an easy challenge in construction, that might be a place where we apply our junior staff. To summarize, and the slides will be available, so this is really just here for documentation purposes or for to make it official. Low emphasis practices would look like this in discovery. High emphasis practices. Now, high emphasis practices are a little different. For the high emphasis practices, we might say if we are concerned about the challenges in discovery, we might want to involve end users more extensively. We certainly would want to talk about doing iterative or incremental delivery if we're not already doing that, just so that we shorten the time it takes to realize or learn that we got the discovery wrong, that we misunderstood what the users wanted. We might want to do user interface or user experience prototyping to get early validation that we've understood the user needs correctly. We might want to do official usability studies. We might want to use senior staff. Senior versus junior staff is a proxy for a lot of good things that happen as we need higher focus or higher emphasis in these areas. And so you'll see me emphasizing senior versus junior staff over and over again on the high emphasis versus low emphasis. Now, the key point here really is just the contrast between the low emphasis practices, where we didn't have to do a whole lot, and our risk was still pretty low because we don't really foresee a lot of challenges coming in this area on this particular project. But if we do see a lot of risk coming in a particular area on this particular project, we can use different practices to actively attack that risk so that it doesn't end up torpedoing the whole project. End-to-end formal inspections, formal modeling of requirements, use cases. So these are additional practices we could potentially employ if we're really concerned about the challenges coming out in the discovery phase or the discovery activity. Now, talking about low versus high emphasis in invention, we already went through the low emphasis points, so I'm not going to dwell on those again. But again, the contrast here to what we can do in a high emphasis way is we can be really active in attacking the challenges if we're deliberate about it. So we could have formal architecture development, we can have proof of concept prototypes, we can do design studies where instead of just people sitting at their desks and coming up with the design as they code, we actually officially consider what are different design approaches, and then we have discussions and reviews of which design approaches are going to work better. We can do formal detailed designs. I think on most projects that's overkill, but if we have a super high challenge in a particular project in the invention area, that might be a case where we want to do that. Maybe we do end-to-end formal inspections on the design if we're that concerned about making errors in the design that might call for that level of formality. Certainly iterative or incremental delivery, which sets us up to detect mistakes more quickly, would be a good thing to add if we're not already doing that. And the use of more senior staff, again, a proxy for all kinds of goodness in terms of needing a higher level of anticipation of issues and a higher ability to address those issues as they're identified. To complete the thought here, low versus high emphasis in construction, we talked through the low emphasis points already. The high emphasis points, and here I've got two slides, but this can include formal coding standards, which hopefully everybody's using already. Test first programming, I think, can be a good practice in general as well. Pair programming, In general, I think that's a good practice to use selectively, but if we really need a high emphasis on construction or we're expecting high challenges in construction, that might be a good time to employ that practice on a more widespread basis. Code stepping, the idea that before we execute the code, we're going to step through it line by line in the debugger, make sure it's acting the way we expect it to, would be another practice we could use. Continuous integration, I mean, most projects are doing that as a matter of course these days, but if you're not, then that would be something to strongly consider. Daily build and smoke test, same thing. Most practices are doing that or have moved beyond that to some sort of automated deployment pipeline. But if you're not at least doing daily build and smoke tests, that would be a good time to think about at least moving to that level. End-to-end formal inspections of construction artifacts of code would be another thing to think about. End-to-end formal inspections, automated unit testing, if you're not already doing that, automated system testing, if you're not already doing that, and then the idea of design for test, where we're actually thinking about test at design time so that we are making the system testable, and then actually setting up full formal regression testing, possibly automated, doing end-to-end inspections of the construction work and the test cases and so on. And then again, as always, senior developers, senior testers, as a proxy for good work across the board in this area. So to summarize, here's what the contrast looks like between low emphasis practices and high emphasis practices. And really this is just intended to give you an idea of really the fact that we don't have to act exactly the same on every project. We have the ability, based on identification of where the challenges are going to come from, to alter our approach so that it is suitable to the project that we're working on. And that can reduce the risk on a project that could otherwise be a pretty high risk project, so that it comes down to be a normal risk project or maybe even a low risk project, because we have actively attacked the project through these kinds of higher emphasis activities that a lot of times teams just don't think about. If they're used to working in a way like this, they don't always realize that they could alter their approaches and work in a way like this. So the key point here is just that you can alter your approach to be responsive to the unique challenges on your specific project. So those are the practice-specific responses. The list is not intended to be exhaustive. You certainly shouldn't be using all these practices on every project or even any project. The point is really just to illustrate that different projects can respond to uncertainty differently. So what conclusions can we draw? I think projects are different. Responses to projects need to be different. And the sources of uncertainty and the degree of uncertainty are huge contributors to differences in how we should be attacking projects. And I think the intellectual phase profile model gives us a useful way to think holistically about the sources of uncertainty and the degree of uncertainty and where challenges are going to come from on our project and our responses to uncertainty. And so that basically concludes my comments for today. I'd encourage you to check out other lectures in this series. As the email notice said, this lecture is based on a lecture from my Understanding Software Project series. Overall, we're going to continue to have these Lunch and Learn series, which you can go to at construx.com/lunch. If you like this lecture, I encourage you to share the website with your friends and hopefully have some good team discussions afterwards. We do have some questions, so at this point I think I'm going to go ahead and look at my question list and see what we've got on the list here. Let's see. So here's a good question. It says, in terms of focus or schedule, how would you characterize proof of concept done as part of the discovery process? On the one hand, it's pure discovery, but management will tag it as construction. How can we distance the two cases? So I think this really is a good question. I think that proof of concept work, by its nature, is going to be let's go back here to the. I'm going to drop this. You won't see the presentation here for a minute, but let me go find the slide here. Proof of concept work. So if we look at where the challenges come from, then proof of concept work, depending on what concept we're talking about, typically is going to look like this kind of middle diagram here, where the challenges are really coming from, or maybe this diagram here, where the challenges are going to come from invention and from implementation, not so much from the requirements per se or the discovery per se. When we're doing proof of concept, really what we're trying to figure out is what's possible and what's practical in the new technology that we're working in. And so we really just have to create our responses based on the expectation that there's going to be some discovery work, especially in the implementation technology, and that could end up rippling backwards into the design or the invention and into potentially into the requirements. So I think, you know, the idea of spikes, I think, is a key idea here, trying to fully exercise the technology so that we have a good understanding of what's possible and what's not possible with the technology. So that'd be the direction I would go on that. I think is just emphasize the concept of spikes and try to maybe educate the management about on proof of concept work. We have to be a lot more deliberate about what we're doing. Aside from the intellectual phase model, I think that another concept that's really important for proof of concept work is I like the phrase of doing the minimum amount of work possible to answer a specific question. And that phrasing is pretty deliberate, the minimum amount of work possible to answer a specific question. We have to have a specific question so that we're not just going off into the weeds for days or weeks at a time. And then once we have the specific question, then we really are deliberate in answering only that question and not accidentally drifting into doing the project itself or doing the implementation work of the project. All right, so let's see whether so some of these questions I think were answered later. What are some examples of high wickedness projects? Self-driving cars. Yeah, self-driving cars, I think we've got challenges certainly in all three areas. And then good question here, is there a correlation between wickedness and research projects? And again, I think in terms of this diagram that I just talked about, indeed, I think that the wickedness is going to come in a research project, depending on whether the research is research into software technology or research in science. If it's a science research project, the challenges might actually come from discovery. Otherwise, the challenges may come more from the invention part. It looks like we have time for one more question here, and I think the question we'll look at is, sorry, just a moment here. I get back onto the right slide. Oops. So this last question is, some authors use the term discovery of algorithms as opposed to invention. Do I object to that? No, I don't object to it at all. I just think for my purposes, I need to keep the distinction clear between what I am referring to when I refer to discovery. And, you know, certainly the concept of discovery and invention are overlapping concepts, but I use those mainly just to refer to discovery, to refer to requirements, and invention to refer to design. And the follow-on question here is, do you think low-level design can be thought of as discovery, or is there a reason to prefer thinking about it in terms of invention? I think low-level design can be characterized as invention, but I think a lot of times the lower-level design, I'm not sure it even rises to the level of invention. A lot of times it's just a matter of thinking, you know, thinking before you act. In terms of, is there a lot of uncertainty in the low-level design? Sometimes there is, a lot of times there's not. And I think when you get to low-level design, if the higher-level design has been done well, then the uncertainty at that point should be relatively modest. So thank you for joining us for our inaugural Lunch and Learn. I hope you found this to be a good use of your time. Certainly welcome your feedback. And you can contact me at the address here on the screen of stevemcc@construx.com, or contact Construx generally at hello@construx.com. Appreciate you taking the time today, and look forward to you joining us for some future session. Thanks.